all information will be there.
We can be wherever you want, as you can see. In 100 years of history, we
Thank
have
you.
been changing.
The floor is yours, Pera.
Thanks. Thanks. So I will take the chance given by Alejandro just to start. Will not extend much here, of course, but we are in a company with 100 years of history, and in short, we are now what we were 100 years ago after passing, you see, for many hands in between. Yes, we were BASF when we started relations with you. We were BASF since it was in 2006. But in 2020, new group was created from this BASF division. And in the end, in what we do, we produce chemicals that are used for the construction industry. We divide this in 3 big blocks. I will start here, because here, at least in Spain and Europe, it is not our, let's say, biggest division. It is our strongest part, and precisely here in Spain, all these technologies that are nothing else than chemical products that are used to produce concrete. Concrete you have seen many times. You will see the ingredients later on, but there is one ingredient that it's almost used always, that it's a chemical admixture. Okay? So we produce these chemicals that are used by cement producers, by concrete producers in their, I would say, daily activities. Okay, so concrete. You all know concrete. Concrete made of coarse aggregates, we call it stones, okay? Cement, water, sands, I will tell you why I have highlighted this, and the chemical admixtures that we produce. There are different chemistries for this, but you see the last one, this what I call PCE, that in the end are polycarboxylates, branched polymers that are based on a normally acrylic backbone, and we do ester, ether, different techniques, but in the end it's a branch polymer, linear chain of carboxylate and polyethylene glycol side chains. These are, in the end, dispersants, cement dispersers. Sorry, these products are used to minimize the amount of water that is needed to produce concrete, let's say with the expected fluidity. If we put too much water in concrete, strength decrease, durability decrease, so in the end we need to find a compromise. The maximum fluidity with the lower amount of, with the lowest, I would say, amount of water possible. For this, chemical admixtures are used. And why I have highlighted sands here? It's quite typical that sands contains very small proportions of clay. Clay means problems for concrete, always. Even I have to say that for sands, there are limitations related to the clay amount, but even below the limits, we can have specific but severe problems related to the compatibility with the admixture. It is something well known, okay? That clays impact on concrete, I would say overall, but specifically they impact on the performance of the chemical admixture. If the chemical admixture doesn't work, the concrete doesn't work. So today it's a key tool to produce concrete, and I'm not talking about punctualities. Almost 100% of concrete produced in Europe contains one admixture. We call it water reducer admixtures, and I think that just with the name it's clear the function of the product. Okay, concrete. You know, concrete is produced in a batching plant, then is transported to the specific job site, with the trucks that you have seen many times, with all the traffic jams here in Barcelona rondas, then waiting in the job site, wait a second, now we need to pump. In the end, it takes time. So the fluidity of this concrete needs to be, I would say, stable within unexpected ranges over the time. By law, I would say, by regulations, at least 90 minutes, the concrete needs to stay stable in a specific range of fluidity, depending on a specification. Okay, what happened when there are, I repeat, very small proportion of some specific clays in sand? Happens something like this. There is a premature loss of, we call it workability, but in the end means fluidity, okay? But as you can realize, it means that, I'm not saying that when this happens, it hardens. No, but it's like something impossible to handle, to manage, impossible to pump, impossible to pour. Okay, not a concrete ready to be used. When this happens, the batch needs to be rejected. So, clays coming from sand in concrete produce a performance that it's not accepted, okay? As I said, it is something well known. Even there are some specifications with some standard tests in order to define if the quality of the sands is enough for concrete production, but even in the cases where theoretically the sand is acceptable, the incompatibility with the admixture in the end means the same consequence at the end of the history. The concrete is not suitable to be used because a too early loss of fluidity. Not due to, I would say, the own water uptake of the clay, because if the content of clay is small, this effect is not really representative. But the incompatibility with the admixture, and due to the role of the admixture in the fluidity of the concrete, in the end, it leads to the same consequence, to premature loss of fluidity. In the end, keep in mind that clays in concrete always means problem for whatever the reason, okay? Okay, I say it is something known, and it has been well studied by many scientists, I would say in the last 15 years, and I would say that even today, for companies like us that we produce chemicals for these applications, it is today the biggest challenge, technically speaking, to be solved. You will see that we have solved at least part of the problem, but it is today even still a topic, okay? As I'm saying, it was studied by many other scientists, and when we talk about clay, problematic clay, we normally talk about swelling clays. You know the structure of these clays, it's a laminar structure, okay, with a space between the two layers, and in the end, it is what is measured. Kaolin, muscovite, these are not swelling clays, and you see when we prepare a paste just with the clay, water, and the mixture, the dispersion, we see no difference when we measure the interlaminar space. Same with micas or muscovite. But with montmorillonites, you can see that with this technology that we call it PC, that I have to say that it's the majority today. There are different chemistries for chemical admixtures for concrete, but I would say 60% is what we call PC. And look, it was already observed by the previous researchers working with that you see that what was observed is that the space between the two layers, when a PC-based admixture is used, expands, okay? It was big observation at this time, because in the end, we start talking about the phenomena of intercalation of the lateral chains, polyethylene glycol chains of these admixtures. Okay? I will show you this, but it more or less represents the structure of the dispersants, okay? Polycarboxylate, PCE, this chain that is a backbone made of acrylic acid, methacrylic, and these linear side chains, methoxypolyethylene glycol, normally it is the shortest, up to 160 units of ethylene oxide condensated, so long chains, okay? So what was the conclusion with the previous studies? Okay, we know that it is the structure of a dryad montmorillonite. It is able to capture more water in between in aqueous media, but when we made this test, just mixing the clay with the water and with the admixture, the normal procedure for this was we prepare the paste, we dry the paste, and then we measure the interlaminar space of the dryad powder. And we see that this distance was changed, okay? And, well, considering all the distance, all the sizes and so on, it fits with this model. The incompatibility is due to one of these side chains intercalated, okay, inside the montmorillonite. Intercalation phenomena, it was called. Okay, sounds more or less logical, but the truth was that, and now I will jump many steps, just to say that what we have seen here that looks convincing, it was not matching with many other experiments. So, first of all, doesn't matter the dosage you use, doesn't matter what we have. When we do X-ray in these conditions, we always land to the same picture. One ethylene side chain intercalated, one. But when we were measuring other things, sorption, fluidity test, it was not matching. Something was missed in between. X-ray, let's say view, was saying that it's always the same, one side intercalated, but looking or performing other tests, that was not the suggestion. And in the end, if we want to study a phenomena that interferes on the fluidity, I don't know how we call it in English, but here we say lo que va a misa. I don't know how you can say it, but it means, what means no discussion is that if I want to study one phenomena that is interfering fluidity, if I measure fluidity, that's the important variable. And all the measures related to fluidity were not matching with the model, with the intercalation model. If we, as chemical producers, need to develop new chemistries to overcome one big challenge of the industry, if you have contradictory information, it's very difficult to decide where you need to go in order to solve this. So it was clear that something was missed in between. Fluidity tests, sorption tests, very consistent between them, were not matching with the conclusions taken, let's say, with the standard methods that we can do in our lab. We are a chemical company producing chemicals for concrete. Of course, we have diffractometers in our lab, but standard equipment, okay, that is used everywhere. And it is what was seen when you perform your test with your current media. Okay, at this point of time, we went to Alba, I don't know, a couple of years ago, I think so, couple of years ago. And in the end, we plan to do something assuming that the information given by the X-ray diffraction was at least non-complete. we discuss, and we finally decide to perform the same test, but instead of drying the paste, clay, water, and a mixture, performing the test directly on the fresh. Here, it's easy. We feel, well, it's easy. It's not easy to fill the capillary, I have to say, but we fill the capillary. With the standard equipment, if we want to perform with fresh, we need to put the paste between the two films. Well, a nightmare. Nothing was seen doing like this. But definitely here we see very interesting things. Look, it is standard procedure, okay? Drying the paste, measuring the spacing. In practical terms, always same result. Doesn't matter the dosage you use. Always same. But when we move to fresh pastas here, well, it looks like that we are really testing different things, no? But the variation of this spacing, it was observed that it was much larger than was observed with the, let's say, classical methods that we have for doing this analysis. Then going in more detail, we even take the information from all the experiences here to do something more or less similar with a classic diffractometer. But I have to say that there are a lot of problems with resolution, so we more or less define an internal method, but I have to say far from what is observed here, that with a spectacular resolution, I mean, it was clearly seen that something was happening that was completely ignored up to now. Okay? So, first of all, strong dependence on the dosage, defining the expansion of the clay, much more expansion that was observed here. And with all this information, we were able to, let's say, fine-tune this mechanism. What was clear is that the clays in water having an structure like you see on the top, and it was the monolayer, let's call it like this, intercalation model that was defined by the previous investigation. Okay, what we see here was very matching with a much complex model of intercalation. No longer monolayer model, but multi-layer intercalation. Just measuring the distance and knowing all this information, we see that even up to 8 ethylene side chains were intercalated in the clay, so it means much larger expansion than assumed by just one layer, the monolayer model. Okay, that was like, ¿cómo se llama quitarse la venda? You know, but opening the eyes again at least. But definitely, if we have to design admixtures in order to overcome one problem, all the things that we were doing, assuming this model were not performing, but assuming this, well, then the picture dramatically changed. And with this, let's say, extended, I will not go through the details, okay? But with this extended knowledge on the intercalation mechanism, then everything fits. The fluidity loss really matches with the profile of intercalation. All the sorption tests had perfect correlation with the multi-layer intercalation model. Okay, and now we can go to lab and design the products that we really were looking for, and we were not able to, let's say, provide efficient solutions because we were wrong in the concept of the mechanism. Here, I mean, and I think Jordi said the same, we came here to do things that we cannot do in our facilities, of course, okay? But definitely, here it was, I say, big hints for us for product development. And well, the conclusion of this, even I have said that it is not a topic, let's say 100% solved, but big part of the problem has been already solved. And in 2018, we launched a new series of products for this. Enhanced clay tolerance, we call it, okay? But these are water reducers, admixtures, specially designed to be more robust against this, let's say, interference given by swelling clays. Impossible to do these developments without the knowledge that we acquire here. And I think that from the industry point of view, it is the best that we can say. We came here, of course we pay, but largely return, okay? And it is a knowledge that we have, and it is not only that we are selling more, we are selling something that others are not selling. In marketing, we use this concept, blue ocean. It means when you start selling something that you have almost no competition, okay? Big opportunity for us. And not only this, in the end, it also gives you a leadership image to the market. I have been the first one able to solve the problem that nobody else is able to solve. For the guys in the industry, we know that it has maybe not a value that cannot be quantified, but definitely it gives you a reputation in the market that, of course, when you can do something that others cannot do, it's... I just selected this history to tell you we have been doing other things with Alba, and now we are doing something, let's say, with a similar approach than this. It is a new topic, still working on this, but you have heard, well, everybody knows about all the concerns, environment, and so on. Cement production is one of the largest CO2 polluters, yes. Almost 5–6% of total CO2 emissions are related to cement production, okay? But it is the material largely used, top one in the world. I cannot remember the cubic meters of concrete per capita, but it's more than 1 cubic meter per each one of us. I mean, it's... So the material pollutes a lot by itself. You see, it's practically 1-to-1. To produce 1 ton of this type of cement generates almost 1 ton of CO2. And in addition, we have to multiply this by a huge amount of tons. So, big challenge. The cement industry is really, well, I would say differently. It is the biggest challenge of cement industry nowadays, and they need to react. If we jump to concrete, and we say, okay, which is the CO2 footprint associated to concrete? Well, 80% is cement. So if we talk about sustainability in construction, we need to talk about cement. The typical cements used now are the top polluters in concrete, and I would say together with the steel in the overall construction, okay? So the industry has already designed new cements, you see, with lower impact. The light cements, well, we will not go in details what does it mean, but this new type of cements, not really new, but this type of cements with minus 15% of CO2 emissions, and these new cements, we call it LC3, that in the end are normally based on calcinated kaolins, okay? But you see that the impact is much lower in this case. Okay, but again, not everything is as nice as it looks, and there are problems that we need to solve. We have cements with much lower CO2 footprint, but with important limitations to be used in the daily activities. remember what I presented about fluidity and time that needs to be transport and so on. Okay, this cement that is the best contributor in reducing CO2, as it, not suitable as it is, it loses the fluidity too early. And in another hand, if we look at the mechanical strength, you see that the development of strength at early age is much slower with these, let's say, greener cements. You have seen in the constructions, they have molds, they pour with concrete, and normally the day after, they demold. If you need to wait 4 days for the molding, for the productivity of the project, it's not acceptable, okay? So if we want to use these cements in our daily activities, we need to solve for this cement this, and for these two cements, the early strength development. And it is what now we are working with Alba, with Miguel Ángel in the University of Malaga, but we have been doing many tests here. And well, we hope this to conclude in the same way than the place, I don't know, but at least we will put everything to do it. So, in short, we came here to do things that we cannot do in our facilities, but definitely also things that others cannot do too, okay? When we generate knowledge, and it was also, I have seen in Jordi's presentation, when we generate knowledge, in the end, we improve we improve our position in the market to create the solutions that we, in the end, want to sell, because it is our purpose, no? But yes, we are happy with the cooperations, and I have to say that even commercially speaking, the return is more than justified. So it looks like that it will not be our last experience here. And thank you. Thank you.
Thank you, Pera, for this another wonderful example of how we can help industry and how industry can benefit from the synchrotron light. So believe it or not, we are able to help industry and to improve the product. That's an important message. Any questions for Pera?
Thank you. There are papers about this absorption of CO2 by concrete during
Yes.
the whole lifetime of the concrete.
Correct.
And is it like serious, or it is
No,
like...
no, it is totally serious.
Okay, are you like tracking that, or maybe trying to improve this? Because I think that...
But the capacity of concrete during his life to absorb CO2, it is well known, and it is basically because concrete, cement, hydration produce a lot of calcium hydroxide, free lime, and it's simply reaction with the CO2 from the atmosphere, and all the CO2 is captured as a carbonate.
Yeah, and it even makes concrete like harder,
No.
yeah?
No.
This is what I've heard.
No, but you're right.
Yeah.
It helps to close porosity, which is something apparently good. But concrete in the constructions, it's not the material. I mean, what we build structures is with reinforced concrete. It means that the concrete has steel bars inside in order to improve, let's say, the behavior, attraction, okay, and all the different efforts than pure compression. These steel bars are stable in a media, high alkaline media, precisely given by this free lime. It protects against corrosion. But when the carbonation depth, so the depth that the CO2 is able to penetrate and consume this lime, transforming into carbonate, of course, it uptakes CO2, but it lowers the pH. And then the rebar starts to corrode. And then the structure needs to be refurbished, in later stage, demolished. But the function, let's say the mechanical functionality of the structure is severely interfere when the pH of the concrete decrease, and the responsible of this decrease is the CO2 capture. So good if we just focus on the environment, but very bad if we talk about the house where we are living, okay? So it's true, there is a CO2 uptake by concrete, but far from being a, a desired effect.
But I have heard that there are also like companies are trying to have the like bio additives, like something related to hemoglobin or to. This is what I've heard, that there are also that.
No, I mean,
like adding something to the
let's figure
composition,
out that we can do something in order to the concrete, to allow the concrete to capture CO2, but avoiding the impact on the rivers.
Yeah.
So it is, all the investigations lines are more or less approaching in this direction. It's true. Concrete is able to capture CO2. That's fantastic. But we need to, let's say, solve the consequences of this CO2 uptake.
Okay. Thank you.
Thanks.
Any other question?
Yeah, thanks for your nice presentation, Pera. Yeah, I just wanted to comment that, I mean, you said that you paid for these measurements, but at the end it was one of the fastest measurements that were done here, because as I remember, it was just in 1 hour. We did all this.
Well, in 1 hour, multiplied by a couple of days.
But
yeah,
I think it was few hours of
because
measurements.
one of the good things that we came here, and before testing, we sit and talk. Jordi also has said. So in the end, I think that what we decided to do was very well planned, discussed by. The problem is when you start testing without knowing what you are really looking for. Okay, good preparation of the experiment is key. Okay, it helps you to really get the data that you need with the minimum, okay, effort. All the tests were fast, if we want to call it like this. But because I think the preparation was really at the level that was
I mean, the
required.
message I wanted to give is at the end, the measurements are not that expensive. I mean, it needs a lot of preparation.
It doesn't matter. I've said that it was clearly returned, so no issues. If it costs 1 or 1 million,
No, but...
if there is return, no problem for the industry.
It was around 1,000 euros or something, or something
I don't
like
know, because we did different things. But it is not the point, I think. For a company, if there is a high guarantee of return, investment normally, it's not a big issue. What companies do not like is high risk in investing. But if the opportunity makes sense, of course, it's not a matter how much cost. In the end, it's, I want to spend this because the opportunity is huge.
Okay, it seems that you're a very motivated industrial user for synchrotrons, and that is why my question, how you became so motivated to use synchrotron radiation, because we are from Poland, and we would like, for example, also to have so motivated industrial users in the country. That is why what we should to do in order to motivate and to make such kind of...
now I'm motivated because the outcome was really motivating.
Yeah,
so
but
maybe it could be different.
But how it was? You just awake in the morning and you decided, I will go to the synchrotron.
No. First of all, you need to know what can be done out of your facilities. And I don't know when, but you organize an event for the industries, just to say, hey guys, it is what we can do for you. And then you know, if you realize that here things can be done that you are not able to do, and plus having a problem in hands that you see, hey, maybe the problem is mine because I'm not seeing, in this specific example, it was clear that something was not matching. And let's say, suspiciously, the wrong point was from the X-ray analysis. Okay, so Alejandro organized an event with the industries, and I say, hey, maybe it is what we need to try, at least trying to do something different that we have done, assuming that here they have resources that we cannot. And then, when you do the first step and you really see that probably you are going in the right direction, then you become motivated, as you can realize, okay?
Yeah.
But definitely, the first point, in my very modest opinion, is if the industry doesn't know, nothing will happen.